Every major AI lab has been increasing prices. Google shipped Gemini 3.5 Flash at I/O. It's 3 times more expensive than Gemini 3 Flash Preview. OpenAI's GPT 5.5 launched at exactly twice the per token price of GPT 5.4. Now, in the middle of all of this, DeepSeek just made the 75% price cut on V4 Pro. So the question is, how does one provider cut prices by an order of magnitude while everyone else is raising pricing? And how do you, as a builder, claw back any of that savings on a provider that's exactly raising prices on you? The answer to both of this is prompt caching. In this video, I want to explain how prompt caching actually works, how DeepSeek's architecture lets them price the way they do, and the practical discipline the Anthropic engineering team published for Claude Code. So these are the rules that decide whether you are paying 90% off or full price on every turn. So let's get started. Okay, so LLM request runs in 2 phases. And the 2 phases have completely different bottlenecks that you need to think about. The first phase is prefill. In this case, the model takes your entire prompt and processes it in parallel. Every token attends to every earlier token. Attention scales as n squared, and the GPU's arithmetic unit can saturate. So in this case, prefill is basically compute bound. The second phase is decode. In this case, the model emits token one at a time. Per step compute is small, but every step has to reread the full model weights from high bandwidth memory. Therefore, decode is memory bandwidth bound. So time to first token tracks prefill almost exactly. On a 10,000 token prompt, prefill is the most of the wall clock time before you see the first token. So if you skip prefill by reusing the work from an earlier identical prompt, you can cut both the cost and latency at the same time. Now, what gets cached exactly? So for every token, the transformer produces 3 vectors: a query, a key, and a value. The query is used once and discarded. The key and value describes how this token contributes to every future token's attention, and they get stored. The key and value depend only on the token, its position, and the model weights. So future tokens are not input to them. So let's say there's a token 5 and it has its k and v vectors. Those vectors stays valid for any continuation that keeps token 5 at position 5. Now, every modern inference engine caches k and v for token it has already seen, and the store is called kv cache. If a new request shares its first n tokens with an earlier one, the kv vectors are byte identical. So recomputing them is going to be a pure waste. So caching is not a marginal optimization. There is a recent paper called Don't Break the Cache, which measured 41 to 80% cost saving across 500 agent sessions on 3 different providers. So it's substantial. Okay, so now let's look at the DeepSeek numbers and how it's able to achieve such savings compared to other providers. So DeepSeek pulls this off through one architectural choice that we know. They cache the KV state to disk. So reading from disk should be slower than rerunning the prefill on a GPU, because disk is the slow layer in every inference stack. But DeepSeek built V2 and onward around something called multi-head latent attention, or MLA. MLA cuts the KV cache by 93% compared to the standard multi-head attention. The cache no longer needs to live in the HBM at all. DeepSeek stores it on what they call a distributed disk array, which is basically a cheap disks pooled across nodes. And the cache is small enough that the streaming it off disk is faster then recomputing the prefill from scratch. So here's why the cache hits price can be that low. DeepSeek is not really subsidizing it. The blog post they shipped along with this feature directly credits MLA for it. Their words, enabling efficient storage on low-cost disks. They are renting disks instead of HBM, and HBM is an expensive part of every other provider's bill. Okay, so that's the supply side. The architecture only helps you if you also know how to keep the cache alive on the demand side. I want to give you practical tips that are going to be helpful if you're using a coding agent or one of these systems in order to be able to hit the cache. Now, most of this is coming from Anthropic's engineers who published a thread titled Lessons from Building Claude Code, Prompt Caching is Everything. Agents are everywhere now. They are moving from your IDE into production, taking actions on behalf of real users. And the moment an agent starts using your tokens, you have a problem. You can't tell which action you took and which the agent took. If there is no identity for the agent itself, there is no audit, no revocation, no scope. So agents need their own identities. That's where today's sponsor, Decode, comes into play. It's a drag and drop platform for authentication and access control. They have built the piece specific to agents, the Agent Identity Hub. Now, here is how it works. Take a Gmail assistant as an example. The user signs into Decode once and grants scoped permission, say read emails, send emails. The agent, say Claude, connects to a Decode protected MCP server with its own token. When the agent needs Gmail data, the server asks a Decode's vault, gets a scoped token back, makes a call, throws it away. The agent never sees the Gmail credentials. Now, sensitive rights like sending an email go through an approval process. Decode holds the call until the user confirms. There are other features like scope per tool, short-lived revocable tokens, client registration, and more. And everything lands in one audit log. This is critical for any agent running in production. You want identity, access control, and a proper audit trail. Check out Decode. Link is in the video description. Now back to the video. To start with how Claude Code structure every request, the prefix is built in 4 layers, ordered from the most stable to the most volatile. Layer 1 is static system prompt and tool definitions, which are globally cached across all sessions. Layer 2 is Claude.md and the project context, which is cached within the project. Layer 3 is session context, which is cached within a session. Now, layer 4 is the conversation itself, which is new on every turn. A change to the conversation layer leaves everything above it cached. A change to the system prompt invalidates the entire request. This hierarchy is the whole game if you want to be able to make sure you hit the cache every time. Okay, so there are 5 different actions that is going to bust the cache mid-session. And if you're using one of these agentic systems, here are the 5 things that you need to consider. And these applies to most providers, not only Anthropic. So number 1, switching models. Each model has its own cache. If you are 100,000 tokens into conversation with Opus and you want to ask a question, which is pretty easy, switching to Haiku is going to be more expensive than just letting Opus answer it, because Haiku has to rebuild the cache from zero. That's why you need to pick your model at the start. If you generally need a different model for a subtask, it's better to just create a subagent. That's how Claude Code's Explore agent use Haiku without touching the parent cache. Number 2, adding or removing tools. So a tool definition sits at the system prompt layer, as I mentioned above. An MCP server crashing and auto reconnecting also counts as a new tool definition. So a bare deny rule for a tool like Bash or WebFetch is going to bust your cache. So even updating a tool's parameter, like changing which subagents your agent tool can call, is going to bust your cache. That's why connect your servers at the top of the session and don't touch the tool list at all. Number 3, timestamps or dynamic data in the static system prompt. Okay, so this is an important one because a lot of people have dynamic system prompts which they update based on the type of conversation that they are having or the type of data that they're dealing with. So putting an in-depth timestamp in the static system prompt could potentially looks like a harmless metadata. However, every minute it changes invalidates every downstream cache hit. So you need to be careful with it. Now, number 4, compact in its naive form. So compaction replaces your agent history with a summary, which is a brand new prefix. You need to use it at natural breaks between tasks, not mid-tasks. Now, number 5 is upgrading Claude Code. So new versions of Claude Code are going to change the system prompt or tool definitions. The first request after an upgrade is going to rebuild the entire cache from the top. Now, here's the unifying principle that organizes most of this and how you should approach it. Use messages, not system prompt changes, if you want to preserve your cache. Okay, so some practical things that you can do based on the Anthropic's blog post. If you need to convey time of the day to the model, don't upgrade the system prompt. A lot of people put that in the system prompt. Instead, insert a system reminder tag in the next user message or tool result. Similarly, if the user edits a file, don't change the prompt. Append a system reminder noting that the file changed. Claude Code Harness does this everywhere. Anywhere the harness needs to update the model on the world, it appends the messages instead of editing the prefix. This way, the cache stays intact. Now, let's talk about the most interesting part from the blog post, where they describe 2 Claude Code features that are specifically designed around the cache. They show what cache-friendly design actually looks like. First is the plan mode. So the obvious implementation would be when the user enters plan mode, you swap the tool set to read-only tools. But that would break the cache on every toggle. So Claude Code instead implements plan mode as 2 tools, enter plan mode and exit plan mode. The tool definition never changes. When the user toggles plan mode, the agent gets a system message in the conversation explaining it's in the plan mode. That way it intacts the cache. Second is cache safe compaction. So the naive way to summarize a long conversation is to use a separate API call with a different system prompt and no tools. That way there are going to be 0 cache overlaps with the conversation you're summarizing. So you pay full price for the entire history again. Claude Code implementation uses the exact same system prompt, tools, and a prefix as the parent conversation and appends the compaction prompt as a final user message. So the API sees it as the parent's last request plus a new message. This way, they preserve the cache. And this primitive is now in the public Anthropic API. So if you're building your own agent loop, you can use the same pattern. Okay, so 2 practical preservers worth knowing here. First, editing Claude.md mid-session does not burst your cache, but it also does not apply until the next /clear /compact or restart. The file is read once at the session starts and held in memory. So if you change a rule and Claude keeps doing the old thing, that is why you actually need to restart it or compact it. Second, /rewind. So rewind truncates your conversation back to an earlier turn. The remaining history is exactly what the cache was built from at that point. So the next request hits the earlier cache entry. The Anthropic team explicitly recommends /rewind or /compact when you want to abandon a path entirely. Okay, so to wrap this up, the reason on the provider side is architecture. On your side is the discipline. Pick your model at the start, connect your MCP servers at the start, leave cloud.md or agent.md alone mid-session, prefer /rewind over /compact. Anyways, I hope you found this video useful. Thanks for watching, and as always, I'll see you in the next one.